Start recording. I don't know if you saw, but I thought maybe we should start quick by going over a little bit about the exams. So let me. So, yeah. So as I had mentioned last time on Monday, the first exam is on September 27. So if you click on the announcement, basically it'll send you to give you the link where you can find the information. Yes, there are those things, exams, which is actually like the official website for the multivariable calculus. So basically you have to go to the end to find the information for this exam. So first of all, if you go to MyLab, you should be able to see some assignments which roughly have these three names. So these are just basically the solutions for those assignments. I mean, there are assignments not in the sense that they will be graded. It's just for you to practice. I mean, they won't be graded. You can practice them as many times as you want. But I mean, they're sort of like practice exams. Essentially, they're like based on the problems from the exams of spring and fall of last two semesters. So they are really like exam problems. So like there are three practice exams like that. And if you want to compare your solutions, like just click on these PDFs. Okay. And then there's also an exam guide, which with a summary of the most important formulas and things like that. So you can also check this out to see like everything that you need to know. Okay. So another thing that's maybe important to say is that, so basically the way in which the exam will work is that, as I had said in the first class, we're going to be using, oh yeah, that's useful. We will be using responders. I don't know if people have used responders in the past. If you haven't, and I do recommend you try this. I think most of this, like for example, I don't think right now it makes a lot of sense for you to try the practice exams. I think that after Monday, we would have covered most of the material for the exam. So almost all of the problems on the exams you would be able to do. So I would wait at least until Monday or of next week to start looking at the exams. If you just want to take it like have an idea, you can wait a little bit longer. But at least there's like an assignment again on MyLab called Respondus Practice or something like that, which is where you have like it's like another assignment which actually does use Respondus, so that you get like a sense of how Respondus works if you haven't done it before. And I also think you have to download like some software for it to work. So, I mean, this I do recommend that you try sometime within the next couple of days, so that you, that should be, I mean, once you click on the assignment should give you like, once you go to the MyLab assignment, I think the assignment will tell you what you need to download. So, yeah, but if that's not working, actually, let me know. Well, I think probably we'll have, I mean, definitely by the end of next week, but again, by the end of Monday, we'll probably have done like 90% of the material. So there's like a very, yeah, kind of, so like we may finish it by Monday, but I doubt it. So like, I would say by Monday, probably would just have like one section left for the exam of the book. So it's still, for this Respondus assignment, there's some solutions if you want to check them out. And it's just so you can compare it here. And so besides that, like the thing that you need to know is like specified here, but like essentially the exam starts at 9 p.m. Once you start taking the exam, you have to go first through Respondus. Once you finish the Respondus stuff, it has both parts. So it does have the lockdown browser, and it should also have like this thing where it's recording you, correct? So it should be both. Yeah. Because it is so that, I mean, it's a long story, but it is to some extent because all the sections of 250 were taken at the same time. So it's the same exam for everyone. Well, that's the thing. So this is the time where you can access the exam, right? You don't need to start the exam at 9 p.m. because the exam itself is 35 minutes. Like the actual exam is 35 minutes. So like you could start at 9:20, for example. The only thing that I was saying is that like the idea is that once you start the exam, I mean, first you start like first you do the responders thing, which I think usually takes like 5 minutes or 10 minutes to get it through. And after you do the responders, then you really have 35 minutes to answer the questions. So if you have a class at 8:50, that should still be fine. You should still have enough time to like, just like, I would give yourself, like, just give yourself like 45 minutes. It should take you like 45 minutes, like between responders and the actual exam to finish everything. And then, yeah, the exam will be 3 problem. Yes, it is necessary to have a webcam. Well, usually I mean, typically, in general with responders, like you get flagged if, I mean, responders, it's not like the best, I think, machine learning software. So you may get flagged for silly things, but you never get kicked out of the exam, right? So it's not, if you get flagged, it's not that means that you get a 0 or anything, or it's game over. It just means that you were flagged, but like eventually one just like, no, you don't also get points off when you're flagged. No, it just means that you may just need to look the instructor, like, you know, depending on how many flags you got. Like, I think everyone will get flagged at some point because, again, the system is not too sophisticated. But I mean, like, if you start getting flagged every 2 minutes, then like probably the instructor would take a closer look at what's going on. I mean, I'm just saying, so responders is not that bad in the sense that, like, I would not worry too much for like, for, yeah, that's one of those like things that if you are like writing, like, you get flagged for, but it's not, I mean, again, the fact that you're getting flagged doesn't mean too much, because like it would not be like everyone would get flagged by for the same reason. So it's just that like some may get flagged above the average, and then like probably you take a closer look at those situations. If you're in a different time zone, then you can, I mean, depending on how comfortable that is for you, you can email me, and you can, like, we can see if maybe the makeup is a better option. But yeah, so I mean, I would not read too much into getting flagged. It is just like it's just to create you know, yeah, the lockdown is not, yeah, it you know, it's just some barrier to people like just blank out cheating. But like, again, it's not the responders will be like, oh my god, you have been flagged 10 times, you'll get thrown out of the exam or something like. So you could be flagged 100,000 times and still you just take the exam. I mean, you take the exam like later, like one wouldn't be. Well, yeah, we'll be grading the exams. Also with our TA. I think you have to show at the beginning the note sheet. Like, right, like there's something about a note sheet here. Like, strictly speaking, like, so you'll have, yeah, you can write like on a piece of paper, a 2-sided piece of paper, whatever formulas you want. You can just write anything that you want. Like, I think you just have to show it at the beginning of the exam, like when you have to show your environment. But it's like, you know, like it's not that like we would read what you wrote. I mean, it is like a note sheet, so like you're free to write anything that you find like important. So but you don't have to upload a picture of the note sheet. Yeah. I mean, to Canvas, if that's what you're asking. Like you may just need to show it at the beginning when respondents like asks you to show your environment. But well, yeah, I mean, like, yeah, the sections are like, the sections are described here. So it's basically chapter 12. Well, it's not open notes in the sense that you cannot use a notebook. It is open notes in the sense that you can write anything like on your note sheet. So, well, like the exam questions can have like, that's just easiest if you just look at the old exam problems, like to see what sort of, like what the structure was. Yeah, the calculator should not be necessary for the problems. So you're not allowed to use a calculator. So for example, like, you know, if an answer has like arc cosine of 50 degrees or whatever, you just write it, sorry. Well, not, depends on what you mean by, I mean, MyLab, for example, will, and now for this, you do have to submit work for the last two problems of the exam. There are three problems, you have to submit your work for the last two. So what I was saying is, like, for example, if you write arc cosine of 50, you can just leave the answer like that. And like even something like 2 plus 3, like that will be recognized correctly by MyLab as 5. So you also don't need to simplify those things. Yeah, you only need to, which will be the last two of the, I mean, two of the three problems, like the last two problems. Well, I mean, there are multiple parts, but again, like it is like, you know, depend, like it is like, it depends like what you mean by multiple parts. Like, yeah, like there there can be more than one box that you have to enter an answer for. Yes. So well, yeah, you should probably, like, once you should look at the old, yeah, I think that's probably the thing that would give you the best idea of what to expect. No, you cannot have an iPad. You have to write like you have to write the problems on a piece of paper. You have to, like, it is more like, yeah. So you have to like do it more like the traditional way.
Professor, if you were to prepare for this exam, what would be your strategy?
Yeah, you should, like, I mean, like you can start with, I mean, not start, because probably you should do that like sometime next week, but you can just like you can look at the old exam problems, like the practice exam problems. And once you do that, I mean, and you completed the MyLab assignments, like I think that's that should be I mean, like that should be okay. The difficulty of the exam is similar to the old exams, yes. Well, arc length in space, we'll do that next week, but it's actually about the length of a curve. No, after you finish the exam on MyLab, you have 20 extra minutes to upload your work. Yeah. Like, What about grammat? I mean, I don't think grammatical errors. Yeah, it's similar. Like the upload process is similar to the same of the quizzes. I mean, there will be like an assignment on Canvas where you just upload your, like you took pictures of your written work and you just upload that to Canvas. Yes, kind of. Is that okay? But yeah, look at the old exams. Like there's also a PDF like here with more problems if you still want to do practice. So no, you cannot use an iPad. You cannot use iPad. You just have to write like on pieces of paper, like your solutions. No, you cannot use the upload is supposed to really be like like the upload minutes are upload minutes in the sense that you cannot keep working after the exams concludes on the problems. It's here on the, you do get partial credit, yes. It's 3 questions. Well, the guide is not on the course. It's not. It's on the link that I posted on the announcement. So you have to click on the link that I posted here. But yeah, like yeah, the exam the exam will appear like as a MyLab assignment at 9 p.m. So you'll see an assignment called September 27 exam or something like that. So it's through MyLab, yes. You just submit your work on Canvas. Like there will be an assignment on Canvas called submit your work, and you just upload a PDF of your you like, or a file where you took pictures of, I mean, similar to the quizzes. That's after the browser is closed. Yeah. You finish the exam on MyLab and then you have 20 minutes to upload the work. Oh, don't worry. I mean, like, there's nothing to be stressed about. Yeah, MyLab, you just entered the answers on the boxes, correct? Yeah. Yeah. But yeah, you can read the announcement. The practice exams do not have the responders part to it. There's an assignment called responders where you can practice the responders piece. Yeah. So you can also see the solutions for that assignment. But there, yeah, if you go to MyLab, there should be something called responders practice or something like that. On Canvas. Okay. So, well, yeah. So that's like something to keep in mind. Again, like probably by Monday, we would have covered most of the sections. Like maybe 13.3 is the only one we would have left, like still having to do on Thursday of next week. But like that should be more like around like 85% of the questions by Monday. So you can read the announcement if you want more information, but like it's just for you to keep it in mind. So Yeah, so today, I mean, we should do 12.5 and 12.6. At least definitely we'll do 12, all of 12.5 for today. So let me start with 12.5, which is about lines and planes. So 12.5 is about lines and planes. And here, we basically start putting together some things we have been discussing up to this point. So how do you think of a line in this class? Well, you can think of a line sort of as a prolonged vector, right? Like a vector that you sort of extended in both directions as much as you want. So for us, like if you have a line, so something like this would be a line. And then the idea is that you can think of a line sort of as like the path that a particle takes when it moves with constant velocity. So you can think of a line as a trajectory of a particle then which moves at constant with constant velocity. And in fact, we'll talk more next week about velocity and acceleration and other things like that. So this is a good introduction to that part. So like you can like think of a line sort of as a road or something like that that's floating in space, right? So it's like it is going to be traveled by a particle or a car. It's just that it will be the car is moving on this road at constant velocity. Okay, so what that means is that, for example, you would take a point here. Imagine you choose a point on the line and think of that as being the position of the particle or the car at time 0. So this is time 0. So there's like this vector that starts at the origin, okay, which we'll call r of 0. So r of 0 is the position of the car or whatever at time 0. And so, and then the car, as I said, is moving with some velocity. So there's some velocity vector for the car, which is supposed to be pointing in the same direction as the line, right? So this is v, which is, you think of a velocity vector. And this is a vector that's giving you the direction of the line. Right? And probably you know this from physics, like the distance is sort of speed times time, right? Or well, let me, like from physics or whatever, that distance is like speed. Sorry, speed is like distance over time. Which means the distance is like speed times time or time times speed. Right? So, if after some time, the car, since the car is moving at constant velocity, after some time t, like t could be 3 hours or 4 hours, like it would just have shifted if positioned somewhere else, right? So imagine that you wait like t hours. So at time t, your position is now here. So this is a position at time t. Right? Sorry, I should put this in black. So you see, like, I don't, how big do you like, so this is a time 0, this is a time t. So how big is like this back, like, you know, there's a vector from going that goes from here to here, right? That's sort of this, you know, there's a, what is this vector? Right, it's a vector, is this brown vector that you see here. This is a displacement, right? This is a vector that goes from time 0 to time t, right? This is like the net displacement. Is that making sense? Of the car in this time. Right, and so how much is the displacement? Like, it's sort of this similar to this formula of distance equals time times speed. It's just that displacement equals time times velocity, is that, if that makes sense. So displacement equals like time times velocity. And so this is t times v. Is that okay? So I'm just saying that the net displacement in time t is t times velocity. So R of t is the position measured from the origin at time t, right? And R of 0 was the position measured from the origin at time 0, right? So there's a vector, which is this brown vector that connects these two dots, right? And that's the net displacement. That's how much you moved along the road. Is that making sense? And that's it. Like, that's all that you need to know about the line. So the equation of a line, and this is what you need to know. And this is called sometimes the vector equation of a line. Is that okay? So let me do an example here. Find the equation of a line. If, well, yes. Yeah, like, right, like next week. Right. Maybe let me do it like as a box. Next week we will learn that if R of t equals R0 plus t times v, then you can differentiate this both sides with respect to t. You see, And you know the derivative of a constant is 0, so the derivative of this r of 0 is 0, and the derivative of t times v is just v, because you're just taking the derivative with respect to v. Sorry, the derivative with respect to t. So this is why this is saying that the velocity, which is the rdt, equals this vector v. But then when you take the derivative one more time, in this case, we will find that that's 0, because the velocity vector in this case is constant, right? So this is saying that the acceleration is 0, which is what you're referring to. Is that okay?
Just a quick question. How come, like, if I'm thinking in terms of units,
Oh, yeah.
the displacement and velocity have different units, but we express them both as vectors. And so
Right. Vectors can be, right. The vector, the velocity has units like, say, of length, like, you know, units could be of miles per hour, right? The velocity vector, correct? And when you multiply this by t, the times cancel, right? So you just get units of miles, correct?
that's true.
And then that's why you can add it with this other vector, which also has units of miles, because that would just be a position. But it is, I mean, vectors can be thought of as having different units, like if that's what you're asking me. Yes.
Yeah, that's what I'm asking. Okay.
Yeah, there's nothing against that. Yeah, I mean, in fact, like later you can think of an electric field as a vector, or a magnetic field as a vector, or other more sophisticated vector fields, and they would all have their different sets of units. It's just that pictorially you sort of still draw them as arrows. So there's no, but that's okay. Like picture, yeah. So they're still all drawn as arrows, even if the arrows sort of, you think of them as carrying different units. Is that okay?
Yeah, that's fine.
Okay, good. And so oh, sorry, and I should say, like, yeah, so if you think of this, well, it's not too complicated, right? This is just the answer. Is that okay? If you wanted to combine like these two things together, so this is like the formula for the position at time t of the particle on the line. Is that making sense? So in general, there's something also called the parametric equation of the line, where you just draw, I mean, it's essentially the same, but you just think of this point r of t. So this is called the parametric equation. Where you think of this point r of t, and let me use another color. As having components entries x, comma, y, comma, z. So this point has entries x, y, z. Okay. So like you just write r of t equals x, comma, y, comma, z. Okay. And then like that just allows you to sort of break this equation into three equations, because like the point of a vector equation, this is an equation between vectors. So secretly an equation between vectors is an equation between each of the entries. So this is just so I haven't done anything magical right now. I'm just saying that the position vector you can just write as x, comma, y, comma, z. And again, like the whole point is that allows you to break it into three equations, where x equals 1 plus 2t, y equals 1 minus 1 plus 7t, and z equals 5 plus 5t. Yes, that's the philosophy of vectors. Between the entries, I would say, not between the inputs. Yes, but right, like, you know, like a vector equation is like a convenient way of writing secretly many ordinary equations at once with cute notation. Yeah. Is that making sense? So, you know, like, yeah. Good, good. So you like typically, and like, again, this is how, if you write it this way, this represents the same line, but this is written in the this is like the same line, but written in parametric form. So this you would call this the parametric equation of a line. Okay. This is usually the one that the course will ask you to write most of the time. So typically this is how you will need to write the equation, the answer. So this is the most used version in this class.
Just a quick question. Is there such thing as vectors and polar coordinates?
Yeah, in fact,
Are we going to work with those?
no, this class ends at 3. Yes,
Okay.
but for example, sorry, just to go back, this equation, right? This equation, like this would actually give you the equation of any line in any dimension. It's just that, like, now, for example, this would have 5 entries and this vector v would have 5 entries, but it would really be the same equation. This would still represent a line in any dimension. So it's just that now instead of x, y, z, you would write x, y, z, w, comma t, or whatever, or w. I mean, you run out of letters quickly, you know, but x, y, z. Let's say if it were 4 entries, you would write x, y, z, w, right? And then the parametric equation of a line would consist of 4 equations. Is that making sense? So yeah, it's on. This is only for a line, yes. But yeah, there's nothing against. I mean, the equation of a line, you can, you know, you can draw lines on the xy plane. You can draw lines in space. You could also draw lines in higher dimensional spaces. They all have like sort of the same format, which is this format. It's just that, like, now you just have more entries to worry about. But yeah, this class ends at entries at 3 entries. Like, we don't do anything more than 3 entries. Is this making sense? Now, and there are not that many things that we're going to do with lines per se. Like, the most typical problem about lines is just finding if 2 lines intersect. So let's talk about intersection of lines. So let's try to find if the lines. So, right, like by intersection of lines, I mean that here you have 1 line, and here you have another line. I mean, in this example, they will intersect. So I'm going to cheat a little bit. And let me draw them like this. And you want to determine this point of intersection, right? Like 2 lines, if they cross each other, they won't cross at more than 1 point, correct? Because otherwise they would need sort of to bend so that they can meet each other again. And that cannot happen because they're lines. They're not, they do not bend, right? So we want to find that point. So find if the lines with equations. And again, like, as I said, like most of the time, this is how the line will be given to you. So let's intersect. Yes, I can scroll here. Is this enough? Or do you need me to scroll more? Good. I see. I think I need to share again the iPad. Yes and no. It's almost, sorry, let me share again the iPad again, because I think it was that up, like, up. Good. It's almost that. Yeah, now it looks good. So, right, it seems like you should just try to set up like the X from the left side with the X of the right side, the Y of the left side with the Y of the right side, and the Z of the left side with the Z of the right side, set them equal to each other and solve for T. But there's just a slightly there's something that you have to be careful about. I don't know if anyone can think of what could be something that could go wrong if you try just to do that right away. Anyone can see a problem?
Well, the X, Y, and Z are different for the two of them, right?
Well, it's more okay. So the thing is that we're asking if, I mean, if you think of this as roads, right? Think of this as roads where the cars are traveling, right? So on the pink road, you have a car, you're traveling on this car. On the red road, you have a different car, right? So even let me draw the cars. They won't be like modern Tesla cars. So they will be very old-fashioned. So here you go. Right? Yeah, and then here you go, right? I'm not asking if the cars are going to crash, right? I'm not asking, I mean, which is what, if you were an insurance company, the only thing you care about, right? I'm not asking if you're colliding. I'm not asking if the cars collide. I'm just asking if there's some time for this car that you go through this point, and then there is perhaps a different time for this other car that you go through the same point, right? So I'm not asking for collision, a question about collision. I'm asking just about whether the paths themselves cross each other. Is that making sense? And you see like the difference? Maybe you can pass through this point at after 7 hours, and the other can pass through this point after 5 hours. Is that okay?
So the position is going to be the same. The X, Y, and Z would be the same, but the T can be different.
Yeah, exactly. You just have to say that the times could be different. So you have to use different variables for the times. Is that making sense? So let me put it like this. So we're not asking for a collision, right? We want to know, we don't care if they collide, if the cars collide. Only if the paths intersect, right? So what you have to do is do what everyone was saying, like you set the equations equal to each other, but you just have to change the variable, like the name of one of the, you cannot use T on the same, on both sides. You have to use a different letter on the other one. So you set the equations equal to each other, but with different names for the T's, right? Oh no, I mean, like that could be fine. It's just that there, like the problem would ask you find if the cars collide. The thing is like that usually has fewer solutions. Like, you know, it's a lot harder for the cars to collide. So it just happens that more times you will not find a solution to the system. So if you just ask for intersection, that's more likely to occur. Like, but change the name of the T in one of change the name of T for one of the lines. So it's fine what we were going to do, but you just have to change. So you can say 2 minus T equals 5 plus, and now let's not say 5 plus 2T. What's another letter after T besides T? It could be, well, S, for example. Okay, and then you say 3T equals 1 minus T, but it's, again, you're no longer allowed to call it T, you call it S, say, and then 1 plus T equals 8 plus 3S. So it's exactly the same equation, right? It's just you just have to change the names of one of the variables. Is that okay? Is this okay with everyone? And if you understand this, then you will always know how to solve these line intersection problems. This is like the biggest like conceptual difficulty on these line problems, because after that it's just like solving a system of equations, which typically are not that complicated.
So I'm still not understanding the full motivation behind changing the variable and why that works, why that avoids the problem from before.
Because now you're saying that, I mean, like if you keep T on both sides as the same variable T, right? That just means that you're sort of implicitly stating that they're meeting at the same time, you know, because that's supposed, like, I mean,
would it be true though?
it can be true, but it's not necessarily true.
Okay.
Like it could happen that they do meet at the same time, right? But if that does end up occurring, you just end up finding that T equals S and will be equal to some value, right?
And then in that case, the equation is saying at time T, the car on the left, or the car on one line is, yeah, I don't quite understand like what the final equation you're, I guess finish solving it and then I might see.
Right. So what, like the only thing that I'm saying is that, like, you know, we're not asking if they collide, right? Like a collision happens if they meet at the same time, right? We're just asking if the, like, if you pass through this point at some time and the other car passed through the same point at another time. So let me finish it, and then like maybe this will clarify a little bit what you are worried about. But so for example, like to solve this system, you can just like say from here, like S equals 1 minus 3T. Okay. And now that you have S as a function of T, then you plug it into the other two equations. Is it making sense with everyone?
Yeah.
And then like now this is not too bad to solve. So what happens with the first equation? It becomes 2 minus T equals 5 plus 2 minus 6T. And the other gives you 1 plus T equals 8 plus 3 minus 9T. And so this gives you, like, for example, what? It gives you 5T, right? Equals what? 7 equals 5, right? And the second equation gives you 10T equals 10, right? So this gives you T equals 1, and then this one gives you T equals 1. So t happens to be 1, and once you know that t equals 1, you get that s equals so from
Why do you have two solutions for t?
oh, this is good. Let me no, it's not that I have two solutions for t, is that I have to make sure that both equations spit out the same value of t.
Got
Because
it. Okay.
if you had like t equals 1 here and t equals 4 here, then that actually is saying that they were not going to meet each other. Is that making sense? I mean, the system was really inconsistent. So you have to keep working with all the equations to make sure that they don't secretly give you different values for t. The values for t have to be the same.
Where did you get that second equation? Because
Uh,
oh, I see. Because you had one in terms of t already, and then you just turned the other one in terms of s.
right.
In terms of t. Okay, got it. Got it. Makes sense.
Professor,
Yes.
quick question. Just to see if I'm understanding this properly. So is the reason why we changed T into S because they never said that the car started at the same time? We just want to know the same spot.
Well, right. It's not that even. I mean, they when they start. I mean, you can always. I mean, t equals 0 just corresponds where, like, imagine each car has its own watch or its own clock, right?
Yeah, that's what I'm asking. They never started like together. They just someone started from destination A and then later someone started from destination B. We just want to see where they meet together.
Where they're right, where the roads meet, right? Not necessarily
Okay.
where the cars themselves meet, right? So we're just asking, oh, is there like in their trajectory a point where both would have been like at the same place, but maybe at different hours, right? You know, it is like, so like even if they had started at the same time, like they could be moving with different velocities, right? And
Mhm.
so like they could still not like see each other because they're moving at different velocities, if that makes any sense. So like we're asking, like you see, if you think about this again as roads, we're asking if the roads meet, but it could be that, you know, when you go through the point of intersection, like, you know, it's like one of like these many roads where like there's a point of intersection, like they just happen to not see each other's, like they are not simultaneously at the same point, like they are just like they go through the same point eventually, but they could go through the same point at different times. Is that better? It makes more sense.
Yeah.
So this is, I mean, I'm just saying, like, if you had kept using t on both sides, that means that you're asking to solve, you're forcing the values of time for both cars to be the same, right? So you're forcing the positions of the car to be the same at the same time, right? So that's what I'm saying, that we're not necessarily asking for. We're just asking, oh, is there like a, by any chance, like happens to be the case that they went through the same point, but is this okay?
Yeah.
Was there any more questions about this? Like, I don't know. This is typically, like, again, this is a typical, like, this is like a typical problem about lines. Like, just like this is actually like sort of like the most complicated problem about lines that you'll find in this class. Like just determining if they intersect, because you have to do the trick first of changing the variables in one of them. If that hasn't been done, sometimes that's done for you, and so then they're more generous. Right, if right. So if you cannot, like, for example, so if you had obtained different values of t, or like, so if you had found, when solving both equations, then there would be no, So, oh, well, the thing is like here, like, so like in the thing you're writing on the chat, like you can use the second equation for to solve for X, and then you would use the first equation to solve for Y. It's just that typically if they're like, there really is 3 equations, right? So I would need to know what would have happened with the third equation to like to see what's going on, like whether or not this actually has a solution. Like if you only, yeah, you have to sort of be aware of all the equations. You can never forget one of them. Yeah. Oh, okay. Yeah, we still haven't, yeah. Okay, so we already found the values for T and 1. Sorry, we found the values for T and S, right? So T equals 1 and S equals -2, right? That's a good point. So, and again, like one of the equations was X equals 2 minus T, Y equals, sorry, 3T, right? And Z equals 1 plus T. And the other was because of X equals 5 plus 2S, Y equals 1 minus S, and Z equals 8 plus 3S. So when you plug in, well, if you plug in the values, right? If you plug in this here and this here, you find 1, 3, 2, right? So that's the point where the roads meet. It's not that they collide. It's not that they collided in the sense that the cars necessarily met. It's just that they intersect. That this is a point of intersection of the lines, right? So this is the point. And you see, it's like it doesn't matter which of the 2 systems you used. Like they both give you the same values for X, Y, and Z, which is what you would expect because like this is like the point of intersection. So this is the place where the lines intersect. Is that okay? Yeah, there can be at most 1 point of intersection, yes. Right, the collision depends on the starting time, right. Which is a different, yeah. Is this okay then?
Wouldn't the collision also depend on the speed at which the 2
It
cars
would
are
also
moving?
depend on the, yeah,
Distance they have to travel.
in the velocity as well, yes. This is like, so the collision depends on more factors, which is why it's more unlikely for it to occur. And that's why typically these questions do not ask for collisions, because then the overwhelming majority would just be, oh yeah, it doesn't occur, you see. So the other part of 12.5 that I have to tell you about is about planes. So you should think of planes as infinite pieces of paper or an infinite sheet of paper. So in fact, this is a good sorry, let me just go to our friend GeoGebra. Can everyone see GeoGebra?
Yeah.
So like, for example, like there are planes like this, Z equals 1, there will like, which is this light blue plane that you see here. There will be another plane like z equals 4. Like there will be parallel, like these two will be parallel. So I'll tell you why they will be parallel. But the idea is that to each plane, you can find like a vector that's perpendicular to the piece of paper, right? Which is called the normal vector. In this case, what happens is that both normal vectors are parallel to each other, like sort of point in the same direction. Okay, but later we like in general, like a plane like has a more complicated equation. It could be something like x minus 2y plus 3z equals 5. So it looks like this now.
So then now we don't only work with the curving of a line, we work with the curving of a vector. So essentially now we're going to be working with surfaces instead of.
Well, we'll work with surfaces in general for the class. Like steel planes are very particular kinds of surfaces because they're sort of not
Flat.
curved, they're flat, right? Like they're not curved, right? But yeah, like the class will work later with more like complicated surfaces. Yes.
Yeah.
Is that okay? And so, so for example, this is another plane like this red one, and you see like in general, if you see these two planes, like for example, this plane intersects this other plane, right? The light. Let me hide the other one. And what do you think? What does like the intersection look like of these two planes? Yeah, they will be lines. So in general, the intersection between planes will be lines. And like if we have time, I'll show you how to find intersection of planes today. Okay. Right. But that's like, if you just keep that in mind, basically you understand like almost everything about planes. So let me go back to the iPad. So yeah, like what I was saying is that if you think of planes as pieces of paper, something like this, a plane, like what we will care about in order to specify a plane, typically what we will use is like a normal vector, n, which is called the normal vector, which is a vector perpendicular to the plane. Okay. So for example, we will say that, like, let me stop drawing the XYZ. We would say that two planes are parallel, right? If they're normal vectors, they don't necessarily need to be have the same size or whatever, but they're normal vectors. Like here, there's a normal vector and there's another normal vector. So you would say the two planes are parallel. If their normal vectors are parallel. I mean, it's a little bit of an overkill, but there's like a quick, I mean, again, it's an overkill, but there's a way to check if two vectors are parallel. What can you do from things that we have learned in this class before? Yeah. Yeah, the cross product should be, it's the same. I mean, right, one is a scalar multiple of the other, but like a fancier way to do that in this class, since would just be to say that their cross product is 0. Yeah. Good. That's one way to verify that the two planes are parallel. So you get a 0 vector when you take the cross product. Is that making sense? And on the other hand, you could have something like this, where you have a plane with a normal vector and another plane with a different normal vector. which is here. And now you would like to say that the planes are perpendicular, right? If what? If their normal vectors are perpendicular, right? Which we can write how? We can say that the dot product is 0, right? Is that okay? So far, so good. Good. So here's the equation of a plane. Let me do it like this. Imagine that you have a point on the plane which you call x naught, y naught, z naught, and you have another point on the plane which you call x, y, z. Okay. Then there's this vector that you can draw on the, like, you know, if you have, if you draw 2 points on the plane, right, which is what I'm doing here, then when you connect them with the vector, when you connect them with the vector, then this vector happens to belong to the, like, sort of be drawn, it ends being drawn on the plane, right? It's like a vector that you draw on the piece of paper. Is that making sense? So what are the entries of this blue vector, right? What is this? What are the entries of this vector, which we have seen before? It's like the vector from point P to point Q, right? If you think of this as the point P. So this is like the vector PQ, right? Q minus P, good. So this has entries x minus x naught, y minus y naught, z minus z naught. Is that making sense to everyone? And what's the property of the normal vector? So the point of the normal vector, it doesn't really matter where you draw it. You can draw it anywhere that you want. You see, but the point of the normal vector is just perpendicular to this blue vector, right? Is that making sense? Because the normal vector is perpendicular to the plane. So in particular, it's perpendicular to all these vectors that you draw on the plane. Is that okay? So far, so good. So if if n is a normal vector ABC, so these are like the entries of the normal vector. and x naught, y naught, z naught is a known point on the plane, what do we know? So you need, in order to know a plane, you need to know the normal vector, right? Like, what's the difference between all these planes? All these planes are parallel to one another, right? So in order to specify them, you need to know their normal vector and a point that goes through them. Because once you know a point that goes through them, you can sort of fix it in space. So in order to specify a plane, you need a point plus a normal vector, right? So a plane needs a, so this needs a point on the plane, on plane plus a normal vector. Is that making sense? Once you give me a normal vector and a point, you know immediately what the plane has to be. Is that okay? So what I was saying is that, like, everyone agrees that n dot pq is 0, right? Well, usually sometimes you are given the equation of the plane. Sometimes you're asked to find the equation of the plane. So I'm showing you how to find it.
Professor, can you please scroll up?
Yes.
No.
This.
Yeah, it just says needs.
Oh, you need a point on the plane plus a normal vector to find it. To find the equation of a plane, you need let me write it here. So what I'm saying is that to find the equation of a plane, let me put it. So let me write it on this side. So to find the equation of a plane, you need the normal vector and a point on the plane. So that's what I was trying to write. Like, those are the pieces of data that you need. Is that okay?
Yep.
And why do you need that? Because, like, what? Yeah, I'm going to show you. In fact, we can, well, I will do a little one which is a little bit more complicated, but yeah, we could do one of like that after I write like what I'm about to write. So yeah, like I was saying is that we know that n is perpendicular to PQ, but n is ABC and PQ is x minus x naught, y minus y naught, z minus z naught equals 0. And then you just do this dot product, so you get a times x minus x naught plus b times y minus y naught plus z times z minus z naught equals 0. Is that making sense? So that's what you get by doing the dot product, right? And so this is the same as ax minus ax naught plus by minus by naught plus z minus z naught equals 0. Is that okay? And so all these things you sort of move to the right-hand side so that the equation looks a little bit nicer. And so the equation of the plane ends up being the following. And this is what you need to know is just ax plus by plus zz equals ax naught plus by naught plus z naught. Is this okay?
Yeah.
So let's do an example. I mean, you'll see it's not too bad. So let's say that the normal vector is like, I'll do one a little bit more complicated than the one on the chat, -1 to 5. And let's just say that the point on the plane x naught, y naught, z naught ends up being like what? 2, 3, 7. Okay. And with this formula, it's enough to find the equation of the plane. It is like, again, this, like the coefficients of the normal vector are a, b, c. That's what you need to remember. So you get minus x plus b, which is 2y plus 5z equals, and then you do like a x naught, so that gives you -2, b y naught, that gives you 6, and z naught, that gives you 35. And so you get minus x plus 2y plus 5z equals what? This is 39. Is that okay? And that's the equation, and that's like more or less how the equation of a plane looks like. Are there any questions so far? So good. Okay, so in general, when you see a plane, like the important thing to notice is that the coefficients, like, again, like the nice thing of how the equation is written in this way is that the coefficients multiplying x, y, and z are the entries of the normal vector. So the coefficients multiplying x, y, and z are the entries of the normal vector. Is that okay? And like I'll do on Monday an example where we intersect two planes and get a line. That's actually quite, that's even easier than intersecting two lines in a way. So we'll see how that gets done. The other thing that maybe I should mention, like, is that you can find the normal vector if you know 3 points on the plane. Right, I'll finish with this. So if you know 3 points on the plane, P, Q, and R, right? Then you have this vector PQ, right? You have this vector PR. And what do you think you could take the normal vector to be in this case? You need something that's perpendicular. Yeah, you still need something that's perpendicular to both vectors, right? And then that's, so you can take the normal vector to be PQ cross PR. So you can also find N if you know 3 points on the plane. So you can find N if you're given 3 points on the plane. Okay. So yeah, next time, yeah, so we're almost done with 12.5. It just, I guess I spent a little bit more time talking about the exam. But next, like the only thing left of 12.5 is just how to intersect two planes, which is super easy. So we'll talk about that. It won't take us too much time next Monday. Do a little bit about 12.6, which is, again, there's not too much in that section. And then we'll start with curves, which is a key topic. So I'll see you on Monday. So by Monday, we would have covered most of the topics for the exam, I think. Anyways, so yeah, we'll continue on Monday. Bye.
Thanks, Professor. See you on Monday.
You too.
Thank you, Professor. Have a great weekend.
Thank you, Professor.